bought it or didn't buy it. So when they purchased this product, and we don't know whether it's 7-Up, Pepsi, or Coke, but when they purchased this product, it tended to be cheaper than when they didn't purchase it. So that's one of those duh things, but now we can formalize it. Yeah, price matters. Price is going to affect the probability of purchase. Duh is good, by the way. We want to look at price. And this isn't a very good, not that it's bad, but basically we want to look at the distribution of prices when people purchase and when they didn't purchase. So essentially what we want to do is we want to put these two together. We want them overlapping. Because we really can't see if the distributions are really all that different. So we know the mean prices are different, but we want to see kind of how different are the distributions. And to do that, we have this simple command. And essentially what I'm going to do is I'm going to overlap one histogram with the other. One of them I'm going to define as when they purchase, when choice equals 1. And then the other I'm going to define as when they don't purchase, when choice equals 0. And I'm going to use the two-way command. So this first line is the one histogram, the second line is the histogram, and then the rest of this stuff is basically going to make it look
So
like...
just the two-way command is what makes it overlap, and the rest is just all the aesthetics?
Exactly, and we did this two-way stuff before when we put revenue and sales. We did it with scatter diagrams, but here we're just doing it with histograms. So again, the red is when they purchased. The not red, the hollow or white, whatever you want to call that, is when they didn't purchase. And essentially what you can see are these peaks when they didn't purchase. You get more observations at the higher end. And when they did purchase, you get more observations in terms of the height of the histograms at the lower end. So we can see that there is a difference in the distribution of purchases. It's not a huge difference. It's not like a real obvious difference. Like you see one distribution here, and then another distribution here, where here's your average price when they purchased, here's your average price when they did not purchase. So we're not seeing kind of this obvious distribution of prices, but we are seeing a difference in the distribution of prices. So for most of these companies, 7-Up, Pepsi, Coke, they're pretty well versed in the law of demand, but I can't tell you how many times this stuff is just like breathtaking. What? More people buy when it's cheaper? Can we win a Nobel Prize for that? I mean, can we patent that?
That's why the average price of a 2-liter bottle of soda is like 99 cents most of the time.
Yeah. And so, but the law of demand is, and I've said this before, the law of demand is not universally, one, known by everyone, and two, accepted by everyone. My favorite is the law of demand doesn't hold for the wine industry. I teach a whole class where we do nothing but analyze wine data and prove the law of demand. Box plots, we know I love those. And we do see some difference. So right, you can kind of see one a little bit lower than the other. The box plot for the purchase, remember these are the interquartile range, 25th percentile, 75th percentile, the line in the middle is the median. So clearly the median price when we bought is different than the median price when we did not buy. Again, just another visual of the law of demand holds. We know scatter diagrams just there's just just not a whole lot we can do with the scatter diagram. So there's our scatter diagram. Use the linear probability model. How much I hate that. So this is our regular reg command. We're going to predict. And we get a straight line in there. We're not going to get probabilities over 1, but we're going to get probabilities less than 0. Again, completely nonsensical. So, and we can see that if we just kind of plug in the formula at different prices, at 0, at 1, and at 3. At the price of 0, probability of purchasing is 70%. At $1, it's 39%. And at $3, the probability of purchasing is negative 22%. You can't get negative probabilities. You're not supposed to. All right. Let's go to the probit model. So what's the command for probit? Anyone want to guess? Probit. Yeah. Probit. Pretty basic. There's our output. This one converged pretty quickly, even faster than the one in PowerPoint. Change in the z statistic associated with the 1 unit change in price. Again, it doesn't have much of an interpretation. It's better not to even try, not to try to interpret, but it's better not to even try to explain the interpretation of these models. It's just going to lead you down a rabbit hole. You're just not going to get out of it for hours and hours. Because then you're going to have to say, well, what's a z statistic? Someone's going to ask, what's a z statistic? Then you got to explain the normal distribution. And then, believe me, I've been through it. Basically, it's negative. The law of demand holds. As price increases, the probability decreases. It's significant, which is good. Price is important. Price should almost always be important. Is always important. We're going to use the same predict to get probability. And again, that's just going to save, what do we call it? Trace hat. And we should be able to get a nice nonlinear. It's not real curvy, but we'll get better ones in the other data set. Yeah, no negative. So it's bounded. It's not going to be. It's not going to go above 1 or below 0. In this, well, it's actually.
And that's the unrestricted model. And it's
Yeah, we haven't.
choice and price.
Yeah, we haven't done any kind of tests or anything like that. But yeah, it's our unrestricted model. Here's a comparison of our probit with our much hated linear probability model. Again, look, it's pretty close for a good chunk here. Pretty close. But this is S-shaped, so it's going to become, as they say, asymptotic to the 0 axis, and it technically goes on forever. And the same with the top. It's going to become asymptotic to the 1 axis and go on for negative infinity forever. You know, and this is why people say, well, you know, a linear probit model is pretty close to the probit model. Why not just use it? It's easier to interpret. I don't have to go through all this z-statistic inverse functional stuff. Don't do this. All right, logit is the same thing. Command for logit is logit. This is the previous data is it's about as easy to use as possible. Let's look at the logit prediction. I don't know, how's it look compared to the probit? We can combine these two. Can you see See they're both in there? Yeah. There. In other words, they're getting really close. So the tails are different. We can see a little bit of difference there. We can see a little bit of difference there. But they're literally on top of each other. So I don't think I mentioned this in the PowerPoint, but one of the distributionally, they're very, very similar distributions. The Logit has fatter tails, and we're going to get some differences, and those differences will most likely be in the table. But the reason they came out with the Logit process in the first place was that it was computationally more efficient. It was faster to run on the old computers where we had the mainframes, where a lot of this stuff started. So the Probit was a little bit more mathematically intense. It took longer time to run on computers. Computer time used to be expensive. So they came up with this Logit process, which is just faster to run. Now, for us, it's imperceivable, the difference. I don't even know if we could observe the difference. Logit instantaneously, and I probe it. I don't know if this is going to be. You
Felt slower.
You can't see if one's faster than the other. So there are going to be processes that are going to make a difference. Margins and margins plots is a lot more useful in our binary stuff. So let's run a Probit. We're going to run margins. Again, we got to specify the range of values, so we're going to go from $0 to $5 per 2 liters. That would be a lot. It'd be like what you pay at the Glenallen Market, which is where I live. And that would be a good deal for you. Oh wow, it's only $5 to get lucky, yes. Notice how much smoother it is. It's a much smoother probability. You can see it's more of that S shape. The one thing that is really interesting here is that it essentially, if we were going to extend this to the, it stops at 0, but if the axis, and this is actually a criticism of Stata that a lot of people have, is that this axis isn't at 0, it's actually 0's here and there. But if we were to draw a straight line up, essentially the probability of purchase runs into about 0.74 or somewhere like that. It goes to what is the implications of that? What does it mean for that y-axis to be at 0.74?
Some people won't buy no matter what.
Exactly. So even at a price of 0, think about what we're talking about, especially the two major brands, Coke and Pepsi. Some people will only buy Coke. Some people will only buy Pepsi. This is what it's saying. Even if you gave it away, not everyone's going to buy it. Some people are always going to buy the other brands. So that's, to me, is interesting in and of itself. Price has an effect. We know the law of demand holds. We saw that with respect to just looking at the prices. But we also know that there is some brand loyalty. I don't drink a whole lot of soda, but when I do drink soda, I buy Coke. I don't know if I've ever bought a Pepsi before. It's strange.
So how did you get that smooth graph?
The margins. So margins is
Just added more data points.
yeah. So the first thing you do is run margins. And I want lots of points because the more points, the smoother. So I have increments. So I'm going from 0 to $5 in increments of 10 cents. Yeah, that's actually pretty high. Usually I use 1 cent. But the graph came out pretty smooth.
Can you insert a horizontal line on the graph to
Yeah.
kind of show where the 1 would, the 0 would be?
Yeah. But yeah. You can try. Yeah, everyone. So let's do this. So let's just do X line. And then margins plots. margin, so that's, margin spots only works after margin, so, yeah. And we can change the color to this, if I change X line, if you put comma, color black, I think it'll make it black. But then you'd still have this little gap. It's just nice if the origin was actually the origin, it's 0. It drives people like me nuts where, why do we have this little gap?
I was just thinking it gives you a better sense of where it actually is on the,
Or an intercept, yeah.
yeah.
Which is the important stuff. And we can find, so, these are, a lot of the commands we use for scatter diagrams, for graphs in general, are pretty similar to ones that we're going to use in margin plots, but margin plot is a lot more powerful. It's newer, so some of these things are different. For example, when we wanted to invisibilize the symbols, we use S parentheses I. Now we have to say it's a plot option, and it's no longer S, it's M symbol I. To add the scatter plot, you don't necessarily have to add the scatter plot, and in practice I would advise not to have a scatter plot. By default, you get these confidence intervals, so if I get rid of the no CI command, it'll automatically, so the default is for it to add these confidence intervals, which are nice sometimes, not all the time. So these are 95% confidence intervals. They might come in handy, but I don't think you want to have them too often. What else is in there? Let's see. And the rest is you got a title, which I got rid of. I put a Y title, an X title. I put a Y line at 0 and 1, so that we can kind of see where the probability of 0 and the probability of 1 are. Get rid of the legend. My standard graph region color thing. I tend to put on everything. Logit, again, is going to look almost identical. In fact, we know they're virtually identical. They're on top of each other. As I noted before, usually I use 1 cent increments, but these seem pretty smooth. Sometimes if it becomes choppy, sometimes if you don't put enough increments, you can get, instead of a nice S shape, it'll just go, it'll get choppy. So this just means you're using too big of increments. So if I used 25 cent increments, I'd probably get a choppy graph like that. If I use 1 cent increments, it'll, the more increments, the smoother it gets. But also, remember, these are all predictions at all those prices. So the more increments I use, so let's run the margins command. So there's the margins command. And there's 51, it's in 51 different prices in 10 cent increments. If I wanted it to be really smooth, and I put it at 1 cent increments, then you're going to get a whole lot more. Again, it's computer time. It's not taking that long. Do a shot while you're waiting. Boom, you're done. So instead of 51, I got 501. But I'll get a smoother graph. And I don't know if this is going to be much smoother or not. It should be, but I don't know if it'll be discernibly smooth. Ooh, that's smooth. That's a close shave for smooth. I don't know if you can tell the difference or not. The other one was probably fine. And these are really the visuals. So, as I said before, and And again, in a presentation, I would exclude the option to add the scatter plots. Looking at that data is just going to distract. What the heck are those dots? Why are they only zeros and ones? Because that's all you have. You either bought or you didn't buy. So just leave them entirely, at least when I do this professionally, leave them entirely. Again, instead of explaining the log of the odds ratio or the change in the z statistic and blah, 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 you can see this is pretty much a demand curve. The higher the price, the lower the probability of purchase. Almost anyone can understand that. So what we want to do is take these relatively advanced stuff. When we saw the PowerPoint with all the mathematical equations on that, we want to take this fairly sophisticated methodology and be able to present it in a really intuitive fashion. And these kind of binary demands is what I call them, I think are the way to do it. It's really the best way to do it, because getting tables of probabilities, and we can do tables of probabilities. That's what we're going to do next. Predicted probabilities, I thought we just did that. So we can do these at, this is just us. Okay, so these are predicted probabilities. Already got the graph. So here I'm predicting margins at different prices. But these are basically things you could almost read off the graph. So at a price of $2, the probability of purchase is 12%. At a price of 50 cents, it looks like the probability of purchasing is 56%. I don't remember what the first one was. At a price of $1, the probability is 38%. So basically all we're doing is kind of doing that. And you can give a table of probabilities, but I still think the graph, the visual, is a much better. By the way, you don't have to do this in, I'm just showing you the hard way to do it. Here's the easier way to do it. You can put all three prices in there. And now we have, right, you can have a table of probability. Price, it goes 50 cents, $1, $2. And as the price goes up, probability of purchasing goes down. The graph tells us that. This will quantify it more specifically. But we're going to have a actually way of doing that in the graph also, which we'll get to. All right, we can do all the same things for logits. So we can evaluate probabilities at, and we just did that. So prices. Remember marginal effects. Marginal effects are the slopes, right? And the slopes are the sensitivity of consumers to changes in price. So we're going to evaluate the slopes, the marginal effects. And again, to get the marginal effects, we're using margins, but we're going to look at the change in the probability of purchasing resulting from a change in price, and that's what that dy dx is telling us. And the price in the parentheses is telling us evaluate the marginal effects of price. It's the only infinite variable. And it's telling us to evaluate it at 3 points. Price of $1, price of $2, price of $3. So what is this telling us? At $1, it looks like consumers are the most responsive. So small change in price is going to result in a 33% increase or decrease in the probability of purchase. At $2, and again, these 1, 2, 3s are, these 1, 2, 3s don't actually refer to the prices of 1, 2, 3. They refer to the first price, the second price, and the third price. But at a price of $2, consumers are less sensitive. Probability goes down, and consumers are less sensitive. Well, we don't know what the probability goes down, but we know that consumers are less sensitive. And at the price of $3, they're even less sensitive to that. So what that's telling us, and what we already know, is that 1, 0, right? At about $3, we're pretty close to here at $3, where the slope is almost, it's getting flat. We know that at $1, we're probably here somewhere where the slope is pretty steep, and then it's getting a little flatter at $2, over here. So if we look at the graph, and the graph tells us this. If we look at the graph again, we're getting those. Let's see, we're getting those insights. Is this the low jig or the probe? So let's see if these conform with our graph. Yeah. Yeah, $1 is pretty close to that 50%, a little bit less than that, but pretty close to that. $2, we said it's getting closer to the flat region, and $3 is getting really close to the flat region. So that's where that sensitivity is. And again, I think it's a lot easier to explain this graph than it is to have this table of predicted probabilities, and then you'd have another table of marginal effects, which basically represent different points along, or different slopes along that function. All right, let's calculate the hit rate. Any questions? Are we lost? Then I'm not doing my job. So I'll try to speed it up.
I'm confused because you said that the 1, 2, and 3 was representing the first price, second price, and third
Yeah.
price.
But he also used those as the dollars.
Yes.
But it's just, yeah, but that's my fault, I probably should. So let's do these ones. We're gonna evaluate this at 50 cents, $1, and $2. And 50 cents is the first one, which you can see there, see the one at. So this is 50 cents, this is $1, and this is $2. So this is just the first evaluated price, the second evaluated price, and the third evaluated price. All right, hit rate. Again, hit rate is the most commonly used measure of fit, or at least measure of accurate predictions. So let's get back to the hit rate. So in the table, the hit rate, which is the one metric, is really the weighted average of the ones predicted correctly and the zeros predicted correctly. But I think these other parts of this model, the false positives and the false negatives, are pretty important too. And it's better to have them if somebody asks for them than to not have them if somebody asks for them. You don't want to have to start doing back of the envelope calculations. Just complete a table. All right, so what are we going to do? We know that. Let's go back to our graph. We know that our probit, we predict, is going to create these predicted probabilities. Remember, the data is literally zeros and ones, but from those zeros and ones, we're going to construct these predicted probabilities. So that's what that function literally is. If we look at, remember when we use the predict command, if we look at the data, let's see. Yeah, so here's choice hat. Oh, that's a LPM. So that's linear probability model. This is the probit, and this is the logit. So we literally took the zeros and ones, and we're converting them to probabilities. So if we take any one of these observations, and the IDs are actually families. So, for example, 7 is, this is a specific family, and we have 3 observations for that family. In 2 of those observations, they didn't buy the soda of interest. In one of them, they did. So if we take one of these purchases, so we need to, let's just take this purchase. So let's see if observation 21, which was a purchase, would be predicted to purchase. So let's look at our linear probability model, LPM, it's 0.14. Our probit was 0.16, and our logit was pretty close to the same thing, 0.16 again. So remember that was a purchase. Is that a very good prediction? So when we test this, when we do our test, so let's make sure we're on the same page first. So we looked at a purchase. And we said that for this person that bought, the model predicted, really they predicted they only had a 14% probability to purchase in the linear probability model and about a 16% probability to purchase in the probit and the logit. What the hit rate does is take our probabilities and convert them back to zeros and ones. And it uses that 0.5 criteria. If you're 0.5 and above, you're converted back to a 1. If you're less than 0.5, you're converted back to a 0. So if we were to convert these back to zeros and ones, what would this person be converted to? A 0, right? Because their probability to purchase is less than 0.5. So we predicted wrong for this guy. They bought, we predicted they wouldn't buy. This would be a false negative. So that's what we're doing when we're constructing that table of probabilities. Did we accurately predict based on the actual behavior? So that's what we're doing. And the formula, or at least not the formula, but the methodology for all that, and it really is a pretty simple formula. The methodology is, do we have them on here? Yeah. So the methodology is here. This is the ones, the predicted ones, or the purchasers that were accurately predicted to purchase. This is the non-purchasers that were accurately predicted not to purchase. What we just saw was a 1 that was predicted to not buy. So that was a false negative. So we just want to kind of construct a table of that. To do that, we got to convert our predicted probabilities back to zeros and ones, and we use this criteria here. 5 or greater, we're going to convert that to a 1. Less than 5, we're going to convert that to a 0. Any questions what we're doing? No, we're going to do it. Hit rate. Choice hat probit already exists. Okay, so I guess we're doing the lows first. Lows is pretty easy. Again, the rest of it is